All right. Hello, everyone. Welcome to our very first ever Center for Learning, Computing, and Imagination Research Seminar, or LCI Seminar for short. I'm very, very proud to introduce our first speaker, Qianou Christina Ma, who is a PhD student at Carnegie Mellon University's Human-Computer Interaction Institute, specializing in human AI interaction and learning sciences, and co-advised by Sherry Wu and Ken Kadinger. She focuses on designing, building, and evaluating LLM applications to help humans adapt and thrive in AI-infused development environments and optimize human-AI collaboration. Her work has been published across top research venues such as AI Ed, Chi, and ACL, and has been recognized by industry and media such as the New York Times. Her research has earned distinctions such as Best Paper at AI Ed and has been supported by NSF, Gates Foundation, and Google Academic Research Award. Without further ado, go ahead.
Thank you so much, Kevin, for the nice introduction. I'm Christina. Throughout my PhD, the key research question that keep coming back to me now as I've summarized is that how can we prepare people to develop some future-proof skills? Gen AI have been developing so fast. What should we be teaching and how should we best prepare them to do so? As introduced, I am co-advised by Ken and Sherry. Ken is providing me the learning science foundations, and Sherry give me insights on HCI plus NLP. So I'm right at the intersection of them, and I do work in computing education and programming. So at the start of my PhD, it was like 2022. At that time, we have GitHub Copilot, like we have multi-line code completion, we have chat-based whole function generation. And then throughout this year, things have really changed. We have IDE integrated AI coding, we have vibe coding, and now we are at really some long horizon tasks, and agents start to be improving on their own. So how does it mean for people to program with AI? And who are programming with AI? Essentially, we see more and more people try to develop some things with AI. As for example, there's this example from the X.com. Some people reported that their 8-year-old daughter started to use Cursor to do some interesting things. And build web applications. And also there's this thing called GPT Store. This is an app store, but for LLM-based chatbots. So people write natural language prompt to create applications such as writing assistant, code tutor, etc., for other people to use. And that's purely based on natural language. And given OpenAI's own statistic, there are more than 3 million of this app launched just within the several months of the GPT Store creation, and there's more than 30K of those creators in a very short amount of time. So many more people are trying to get into developing and are able to produce these applications with generative AI. And we see all these terms, the buzzwords, if you say, of what is important to learn about and how can we work with generative AI to program. There's this word, for example, prompt engineering that occurred like early stage, and then it come into context engineering and harness engineering. Now we have loop engineering. But this is all like just buzzwords that are floating around. However, if you just look at the overall picture, like from the abstract angle, no matter how LLM have changed, how this fancy AI tool have developed, we always have the human needing to deal with its input and needing to deal with its output. So this layer is not gonna change no matter your context, you're engineering the context, engineering the loop, or the very beginning, just the basic the prompt. So I have work that is focusing on each of this area, and today I'm going to cover this two essentially to kind of give you a sense of what can we teach and how can we teach in this communication and evaluation aspects. So first, with regard to evaluation. Apparently, we need to deal with LLM mistakes. So as AI generates your code, it also generates mistakes. You cannot guarantee that it does not make mistakes. Even though it does not make many simple mistakes, like for example, in the CS1 context, in your first introductory CS course, GenAI capacity have evolved to the extent that it don't really make mistake much if you have like a very well scoped out question. However, it is still important for students to develop a sense of like how do we deal with AI mistake, how do we debug. And debugging have been historically just a challenging topic to teach, especially in CS1. We have literature like starting from the 1960s trying to figure out how do we teach debugging, and some things like an explicit debugging cognitive process model may have helped. However, instructors really have difficulties creating all the materials needed for them, not to mention like customize it for like different languages and courses. And also they just don't have the time and resources to evaluate, to like grade, and to create these materials for the students. And a student, as a result, they learn debugging in the wild. I think if you had taken some CS class in as a major or some courses, you may have experienced this, that you have to learn debugging in the wild. You basically do your homework, run into bug, painfully trying to solve it, and then with experience you get better. However, there's no devoted instruction with regard to that. And so we need something that is more easily generated, engaging, and can provide deliberate practice in debugging for CS1, and can we use LLM to do it? And so the overall research question is that can we use LLM to help CS1 students develop debugging skill? And if we have an LLM, can it produce these materials, and can this instruction, we call the system hippocampus, in the end help students achieve a better outcome? And so debugging in our framing, we frame it as like a hypothesis construction process. And we can just look at this example to give you a more concrete sense. It is a complicated process that involves like, reading code, finding bug, trying to fix the bug. But what is according to the literature, the most difficult part of this is like finding what is the bug. And so for example, CS1 problem like that, you typically would have for a test cases like a search statement that specify the input, specify the expected output, and check whether the actual output produced by this function match with the expected output. And to some extent, this test case is a hypothesis of what can go wrong in your code. It's an expression of an expected behavior of your program, and by running the test suite, it's like running an experiment on your code to verify if any of this hypothesis go wrong. So we frame our learning objective in terms of the debugging as a hypothesis construction process, and specifically we designed it to be comprehensive hypothesis construction, aka can student make test suite more complete, and accurate hypothesis construction. Given the test suite, can we map it to a particular mistake? And we design a learning system accordingly, according to the debugging process model that framed this as a hypothesis, construction, and verification process. We have our learning objective and the student's interaction mapped to this cognitive process model. For example, for comprehensive hypothesis construction, we have students trying to make the test suite more complete. And for accurate hypothesis construction, we have the student try to correctly map a bug explanation to the bug. And overall, this is a teachable agent framing, which means the actual human student is role-playing as a teaching assistant. They are trying to help LLM simulated student debug some mistake in the code that they produce. And just to give you some very brief highlight of the system interaction, and to introduce some, highlight some the takeaways and findings. When the students get into our training system, they will see this office hour queue chatbot simulation. They will see like a bunch of LLM simulated students waiting on this queue, and when they get into this student interaction, they will be presented with a buggy code and this AI student seeking for help. And then the students will be asked to construct a test suite or their hypothesis set of how would a given problem go wrong. They can drag and drop the different hypotheses into groups. They can name them, and basically this is a process for them to elicit what type of behavior should they actually expect from the program. And we have the student trying to select the test case, select the explanation mapping to the test case. Depending on their correctness, the system will provide different feedback. If their selection is correct, we will present this the before and after diff view of the code edits, and the LLM simulated student will be like, oh, okay, I see, I've made according changes to my code. However, if their selection is incorrect, the LLM simulated student will act confused and be like, oh, but the program expected behavior should be like this. If the explanation, if the bug should be fixed like this. So given this different feedback, we have this the student workflow mapped to the debugging process model, and we have the LLM generating materials corresponding to each step to kind of supplement this material for the student to complete the activities. And in overall, the idea for the system is that it's a teachable agent that help novice from CS1 to learn hypothesis construction. And we have LLM take over the code writing part and the code fixing part, and have human deliberately practicing and focusing on finding the bug, constructing the hypothesis, and mapping the hypothesis. And some of the use of LLM that may be interesting in our system design is that we reformulate the task to some extent. Recall that we provide this list of explanations to bugs as a drop-down, and there's like one correct option, two incorrect distractors. And the way, in order to make LLM generate authentic distractor, it is very difficult because there's a lot of constraint to that. You have to make the distractor commenting on some similar but different buggy concepts, and LLM have a difficult time come up with alternative plausible hypothesis. However, one method that we find effective is to reformulate this task as follows. So basically, given some buggy code, we can generate explanations corresponding to each of the buggy code, and we can edit it to make sure the explanations are right, and we can cluster the buggy code depending on their performance on your test suite. So depending on their pass-fail behavior, you can cluster them in terms of how similar their mistakes are, and you can then pick, for any buggy code, you can pick the similar, the adjacent but different buggy code, and use their corresponding explanation as the distractor. So by reframing the task of generating distractor as combining with some automatic selection algorithm, it's actually making the task easier for LLM to do, and thus we have we are better able to generate the materials that we want. And when we are trying to evaluate student learning, because our goal is the hypothesis construction, we also have pre-post test items specifically designed for that. So basically, we have a question giving student a test suite and asking them which test case make the test suite more complete. And we also have buggy code and with a test case behavior, and ask them what is the actual correct bug explanation mapped to the code. And the result of this system is that we see students significantly improved in their accuracy and efficiency, and we also see that they believe that Hypocompass is more engaging, fun, and less frustrating than learning debugging in the wild. Note that this is not a controlled experiment, so this is a proof of concept that Hypocompass work as a method of instruction. LLM can help people learn debugging, but it's not to say that it performs better than some state-of-the-art alternative, because the state-of-the-art frequently is there is no instruction of debugging in CS1. And also we evaluate on the LLM generation, which is 4 times faster than human generation, achieve 90% accuracy back in the day. So now it may be even better. some qualitative quotes from participants. People think Hippocampus is actually surprisingly fun, super cool, and want to see it in class. We actually have some classroom using the system as well. So they've been kind of using it just as a method to help people realize that, okay, this is a method you can use to build test case, test suite, and do a more test-driven development. And some takeaways I want to highlight. Yes, question?
On the previous slide, what exactly is the generation?
Yes. So if we go back to this diagram, we have generated a bunch of different LLM materials corresponding to each step. So the generation included, for example, hint for test cases student generated, a hint for test categories, and also the buggy code. So all of the code that are buggy are generated by LLM as well, and the explanations to the bug and a fix, like the corresponding fixes.
So essentially generating the exercise.
Yes, all the exercises.
Thank you.
Yes. Right, and I will welcome questions during the talk as well. I will pause in between the papers, but if there's question, just raise hand. One important takeaway I would like to highlight is that this teachable agent framing is helpful to create an error-tolerant environment and actually give students this premise that they need to deal with LLM mistake. So it's putting students, giving them a mindset that, yes, LLM is going to be wrong, and you are responsible for fixing it. And I believe introduce it as early as CS1 will be helpful when the students are dealing with more and more capable AIs as well. And also this role play is just giving them some sort of self-efficacy buffer because it's not them making mistake, it's the LLM making mistakes. So, and they can have more deliberate practice opportunities fixing multiple mistakes and see how the same problem can be faulted in multiple different ways. And another aspect is that here we are making people deliberately practicing on finding bug and hypothesizing by constructing the test cases and mapping test cases to bugs. We are taking away all the process that involved in debugging, such as like writing code, such as fixing the code, because in order to have people develop some skills efficiently, you need to give them plenty of practice opportunities with repetition. So by designing this task delegation where LLM take over the code writing and human practicing on debugging, evaluating, this is in alignment with the task delegation we believe will be more useful for the students in the future and help them cultivate this evaluation skills. And so that is the paper on evaluating LLM mistakes, the TLDR, is that we can do that via training accurate and comprehensive hypothesis construction. And next, I'm going to talk about my work in communication, by how can we help people better communicate their requirements. But before I go there, any question about the first work? Yes?
Yeah, I thought it was very interesting that you generated all of the code and then group them based on the test suite results. And I was just wondering why you think that it's difficult for LLMs to generate the explanations or like the alternative buggy codes that are similar. Is there some intuition behind that, or?
Yeah, we've tested that. LLM cannot do that job is the empirical reason, but also it's hard to create distractor generation. It requires so much more deep understanding about what is the concept currently wrong, how are the students often wrong, and that's not necessarily in LLM's training data. It's something that an experienced instructor like Kevin may have be able to tell you that, okay, this is the problem, these are the common ways that students are wrong. If they make this mistake and then fix it in the wrong way, they are thinking about something else. But LLM may not have access to the material, so therefore generating a distractor is hard. And there are some literature in terms of, for example, automatic multiple choice question generation, and generating distractor is always hard. Yes.
Thank you.
Any other questions? Yes.
I'm curious, like, so you conducted this study and presented it in 2024. Do you feel like the state of the world has changed since then with AI technologies? And, or especially, I think there are like elements of your theory building, which is like breaking down this is an important skill versus this is not as important of a skill, right?
Yes.
And the offloading. So I'm just kind of curious your general reflections on how the world
Yeah, totally. So as I presented in one of my first slides, there's all this evolution of the different engineerings you could do with AI, right? So what the field perceived as important is shifting. But I think the overall, in the abstract level, people will need to evaluate AI output, and that's for sure. Whether they need to evaluate it in terms of the CS1 context, in terms of like designing this individual test cases, in terms of Python assert statement, dealing with different type of input, that is up to question. However, you still need to come up with hypothesis in order to verify the program that you produce is like living up to your expectation. So if I'm vibe coding, even though say I'm a lawyer, I want to vibe code a tax assistant agent, and somehow I would need to be able to verify if it's performing right or wrong. And that is constructing hypothesis as well. It may not be manifesting in terms of Python assert statement, but either they will be needing to be able to comprehensively and accurately map out this hypothesis space about the output that I care about. So test case is one way for this to manifest and understandable by a CS1 student. So this is this application, but I think the overall framing and the theory behind it is more extensible to more advanced use as well. And we are going to talk more about requirement-related use in LLM app development afterwards, too. Any other questions? Okay, seems good. So with this project, when we are trying to better communicate with AI, this is with the premise that a lot of current instructions on prompt engineering, or even like now the loop engineering, there are aspects that can be automated away and should not be what humans are focusing their attention and energy on. For example, people may make trivial wording change and think that might influence the behavior. They may add some random prompting hacks and say, my grandma is sick, or it's really important for me to hope that this changed the LLM behavior. They may also make some repetitive emphasis and think that improved the LLM performance. However, there's this prompt optimization literature within NLP, and they're trying to think about how can we automate this aspect. However, there's aspects in this prompt engineering process, or rather the process of communicating and specifying input to LLM, that is not going to be replaced by automators. And that is when people is trying to provide customized requirement that is outside of the model distribution, outside of the model defaults. For example, the human need to be able to generate and refine the specific requirements for the goals they want to achieve. Sometimes they make mistakes as well, especially if the requirements they write is long. For example, they may want to have a specific multiple choice question, and then the example they are giving is like a free response text. That's like a conflicting requirement that might confuse LLM as well. So this is the task delegation that we are thinking of. We are proposing this requirement-oriented prompt engineering, or ROPE, as like, again, LLM will focusing on handling the non-requirement aspects, while human focusing on generating and refining requirement. And this concept is not new in, say, software engineer. Requirement engineering is a field on its own. However, it is helpful to adopt this framing when we are thinking about developing with AI, and spec-driven development have been something that people start to talk about too. And so essentially when people, and especially end users, want to develop with AI, they can use natural language prompt to write out all the requirements they have. For example, they want to write a writing assistant. They can specify all the styles related constraints. This becomes an essay of requirement for LLM to execute. To some other extent, you can also call it a prompt program. Natural language programming is, again, not a new concept in PL. Programming by example is also something people have explored. But again, applying it, revisiting the ideas in the Gen AI era is helpful. And we are trying to think about how can we design the goals and instruction that connect these dots together. So with writing a prompt like this, people can power this LLM-based chatbot, which is a program as well. And so the research question here is that can we help end users better prompt program LLM via training on communicating requirements? And the task we asked them to do is to be using prompt to reproduce customized softwares, customized applications. For example, a customized chatbot or interactive game. So they need to use natural language prompt to write out the requirements, try to reproduce this artifact presenting to them as close as possible. Note that for now, you can probably take a screenshot of this and be like, oh, rebuild me this application, and that's done. However, for testing purposes and verification, we ask people to only use natural language to specify out the requirements. And our training system, again, provide people with deliberate practice and feedback, helping people to elicit and specify these requirements comprehensively and accurately. So for example, this is our training system that have apparently a 3 columns design again. We have a chatbot that provide people feedback on their prompt, each turns of the requirement, whether that provides some accurate or is it providing accurate requirements, and is it complete yet? And then we have the middle column, which is a working document of people's specifications so far. So this is trying to summarize the requirements that a user have entered and present it back to them as a working example of, oh, what is a good spec document may look like. And then we have the output panel, which presents to people what is the actual output that may get compiled from your current prompt as a feedback. For example, if a person make a mistake, such as a very naive one, instead of 8x6, they say 6x8, we can generate the actual output given their current requirement, and they can compare it with, compare my solution comparing to the expected output in order to make changes. And so with the, for the pre and post test, we measure these 2 metrics, which means it basically just means that we measure both the input and the output. So we will look into the prompt that people have written and try to analyze what requirement have they covered and have they write about it correctly. And we will also look into feed this prompt into LLM to generate this program and evaluate whether this program actually behave and implemented this requirement correctly. And the study design, now we have a control, we have the system and control comparison, and the control condition essentially is just how people may learn about prompt engineering these days on their own by looking into YouTube tutorials and have some self-practice time with ChatGPT. And the result here, we find the system condition improves significantly more than a control. You can also even say it's a 20 times more learning gains just because the control condition did not learn much. And the system condition also make more edits on the requirements in iterations. So when we try to look at the next prompt edit that it will make, they tend to make it about the requirement more specifically versus the control condition may exhibit some behaviors we talked about in the beginning, making trivial wording changes, making trivial structural changes, and like making non-requirement edits and adding prompting hacks. Some qualitative quotes to give you some context or aspects. The system condition participant would say, oh, this is very easy to understand. I actually see how requirements is influencing my output, and I can organize them and easily revise them, versus the control condition. People may say, I get frustrated with AI. I get frustrated with my communication skill. I cannot get it to do what I want to do. And another result we want to share is that what if we just pass everything to the optimizer? There's apparently all the fancy optimizer people have developed. Can this close the learning gap we have achieved with the training system? And TLDR, no. We passed a prompt that students have written to Optimizer, which indeed, yes, improves significantly on the scores, the requirement, and the output scores. However, this Optimizer may add a lot of things such as chain of thought, format, paraphrase requirements. Sometimes it also adds mistakes, unnecessary conditions, unnecessary requirements that is against the wish of the user or against the ground truth of our task, and that the significant learning gap between the system and control condition is still there. And we also try to see if the better input means better output, right? So we calculate a correlation between the requirement quality and the output quality. And this gives us an angle to understand how ROBE will stay relevant when LLM is becoming more powerful as well. So we've tested it on both GPT-4o and GPT-3 mini, the reasoning model. And we find that with more powerful LLM, that basically just improved the task instruction following. So it make a more faithful reflection of the quality of the requirement people actually write. So if people can get better at writing requirements, these models can also implement better things with a higher correlation, with stronger alignment, and the learning gains that we found in the system still persist, even though we passed this to a more powerful LLM as well. So the takeaway here for this one that I wanted to highlight is that, again, we have deliberate practice, training in alignment with the task delegation. We believe that a human should be focusing on generating and refining these requirements for AI, and this non-requirement aspect can be automated, and we design our training system correspondingly as well, where human practice and receive feedback on specifying requirements and offloading the code writing and prompt optimization parts to AI. So the TLDR, what and how can we teach for AI-assisted programming on communicating requirements? We can do that via training on accurate and comprehensive requirement specification. And combining with the previous output, you can see that for some reason it's all accurate and comprehensive construction of something. It's either the requirement or it's the hypothesis space. But they may be the two sides of the same coin because they are both specifying the behaviors of the program that you're trying to align to. Yeah, any questions for the second paper or in general? Yes?
It's kind of a general question. We've got 50 years of experience in programming languages that English is a terrible language for specification because it's very ambiguous and all that. And so now we're basically, disclaimer is I'm not an expert, I don't know this stuff at all, really. But it just seems to me that we're trying to make English sort of more precise, but less error prone, but somehow we're kind of missing all that understanding that in fact this is not a good language for being precise about anything. Is there any, maybe that's just kind of against the way the world wants to work right now, but is there any insight of that? Is it worth trying to teach people to be a little more how to say things precisely as opposed to sort of stylized English?
Yeah, so definitely. So there are different ways to provide your requirement. Natural language, English is one way. Test case, another way. Writing, there are like, say, domain-specific language designed for writing specification, which is an attempt to make a bridge between the more technical details, syntax that people need to remember versus the natural language, which is too ambiguous. There's also, currently, people can do multimodal. You can use visual to specify your requirement, or you can provide, say, diagrams, sketches, examples. All of these are ways that people can express their intention and requirements. Each have their pros and cons. Natural language, ambiguous, not good for preciseness, but it can be efficient and it can be widely understandable. So people do not need to have, spend 4 years in college learning about Python and all these concepts in order to use natural language. However, they do need to be able to realize there are ambiguity in natural language, and if LLM may make a mistake because of the ambiguity, they will need to be able to get more specific. So there are pros and cons for each different ways where you can specify and communicate your input, and natural language is just one of them that is becoming powerful or easily accessible by others now. Yes.
Kind of also related to the previous question, my question is also very general. When you design your study, how do you decide when the appropriate intervention is to train the human versus when it is to redesign an AI system? So it was great, wonderful, but generally my feeling, not regarding your study, but generally, sometimes we place the burden on less experienced learners to compensate for the limitation of the AI system. So my question is regarding deciding when is the human or the system that you are going to intervene.
I'm not sure if I can share a backup slide. I can, okay. So there are research in all aspects of, say, from tools to human to the interaction, right? Back in the calculators age, we have probably research to like, how can we make calculation better? We have, in the HCI, in the human and this tool interaction, we have HCI research of how can we make the interaction better. And in education, we also have research of how do we better teach math, how can we teach people better use these tools. So I think in generative AI, it's similar to the extent that there are effort invested in all three angles, and each of them kind of bring different values to the field. And it is effective to both help the human to be equipped for the AI, and we are not trying to accommodate for the AI's lack of capacity. We're trying to expect for more and more powerful AI, what skills will stay relevant. And some of this that we are proposing in today's talk, including that you need to be able to construct a hypothesis to evaluate AI output, and you need to be able to specify the requirements to communicate what you want to AI. And that is going to stay relevant when, despite the AI model capacity updates. So the AI can go ahead and do its thing and try to improve its accuracy, but the human aspects, when they are trying to use the AI and interact with it, will stay relevant in that regard. So I think the research in all of this, across all of the spectrum is valuable. My personal interest is in how can we better improve humans and the interaction. Okay. Any other questions? Yes.
A quick one. So what I have been noticing for the current state of art AI systems, they are making a lot of decisions on behalf of you and ask you to verify, even for the tests and for the requirements. Now, if you're using Claude will come up with a requirement first before, even before you send your requirements to it. It will make a lot of assumptions what to be included and what not to be included. What I notice is I myself is a limitation to look at all the docs generated by the Claude. I don't have enough capacity as a human brain to verify so many docs in the morning, like 20, 30 docs in the morning. So it seems, especially for students, for undergraduates, I think they will be overwhelmed even more. And I think that's a problem now. How do you reflect on that? Because your research is mostly foreground. Okay, we need to let the people to ask questions, teach AI what to do in the beginning. But now it seems we are pushing that to the back end. We have to do a lot of verifications, and I doubt whether students can do that.
Yeah, so verification is the aspect when we are dealing with evaluation, right? So yes, you can make AI generate a spec, and then they can fill in a lot of defaults. However, AI defaults also have its bias, and when you have especially customized commands and you want to implement, and if you don't specify that, so the problem is under specification, that can lead to AI output that is unexpected or against your wish. And then how are you able to catch that mistake or verify it? So depending on the output that you try to achieve, right? If you're just okay, I'm a product manager, I'm trying to prototype this thing really quick. and I don't care about like all the different design choices that I may take alternatively, or the architectural choices, etc. And to their purpose, it's fine. Their verification list is short. It's basically some aspects of the interaction they want to demonstrate, or some sort of the technology capacity they want to be able to interact with. However, if it comes to, for example, applications in security or applications in somewhere else where there are certain aspects of evaluation that become important, then people need to equip the skills in order to evaluate AI and to perform the verification. And that requires expertise. People cannot say, generate this Python assert statement if they don't know about like the input and output type, etc. So there are going to be prerequisite skills and expertise involved in producing this verification. And that is just dependent on like the end outcome you try to make the students achieve. And for sure, we don't want to like overwhelm the students. That's also why when we are dealing with end users and like CS1 students, you can see my systems are all very scaffolded, and that's because they cannot deal with more complicated input, and sometimes hide away the complexity is helpful for them to learn faster. So as this instructional designer, once you're clarified on the goals, how to deliver the instruction to help people achieve that goal more efficiently is a separate design question. You don't necessarily expose them to all the real world complexity. You lead them to there eventually.
Follow up.
Yes.
This is what I have been thinking. I need some of your feedback. It seems there's two approaches. One approach is to design a tool for people and for students to think with the tool so that they can understand before, to have more, in my mind, they need to do more cognitive work, and the tools are helping them to do more cognitive work. And another sense is the modern state of art tools, which is we don't need to think everything clearly. We can be ambiguous. We can use natural language. But we need to do a lot of verifications at the end, even if we don't know the specification in our mind clearly in the beginning. I don't know whether if that's a good skills for people to learn, because in the past it might not be opportunities for them to learn the verification before they actually build up their cognition and understanding in the beginning, right?
So I think what you're describing is that people build different things. You generate different things. Previously, you may generate code. You generate it step by step. You as a human will develop this code chunk by chunk and piece things together. You develop your natural understanding of this program along the way. Now, generating code suddenly seems so easy, but you need to generate verification. So it's like different aspects that people are focusing on. And is it easier to that now I'm handing you over an open source repository, and suddenly you need to make sense of it. And if I ask you to do like a feature update, you need to be able to do it and be able to present your decision, etc. It's not trivial, and it's also an authentic task that you may do. However, this may be not everyone will get to develop this software step by step. They will be handing over some existing stuff that already exists in the, especially like produced by AI, and then they need to be able to evaluate it. So that's why I think the emphasis of the instruction or the time we spend on teaching, we can help people practice this verification more. Than trying to build the software from ground up bit by bit. That may be an effective way of teaching verification though, because sometimes the best way that you are able to be a judge of someone is to be able to do it yourself. So whether you're able to get to whether this is a good learning exercise or not is like a design question, but the end goal need to be clarified. Do you want a student to be able to build a software without AI on their own, or do you want a student in the end be able to be responsible of some output that they generate with intelligent tool support? But yeah, so in general, I guess as a review of the research, some of the research that I've done, out of the question that I've been asking, so there are works that is more focusing on the what to teach aspects and also the assessment aspect as well. So for example, on what should we be teaching about working with AI, I have literature review and also like classroom study, trying to elicit the learning objectives out of these investigations. And for how to best train people working with AI, Hippocampus and Rope is the two papers I talk about today. I also have a game-based system that try to teach people about the importance of underspecification and how AI generate bias and default to biased behaviors when you are underspecified. And I also have some works that is more focusing on like the evaluation aspects, like how can we assess people's ability when they are working with AI, something like better than LeetCode possibly. And the current takeaways that I have from my work, if you remember anything, maybe walk away with this slides. For what to teach about programming with AI, we want to focus on, or rather working with AI in general, focus on this higher order thinking skills of communication and evaluation, make sure the students can provide good input to AI and deal with its output. And how to best train people to work with AI, we found it effective to design systems and instruction that is aligned with the task delegation strategy you want to achieve. And scaffold and offload a lot of irrelevant parts of the steps of the interaction to LLM and to other tools to your learning system as well. And for how do we assess people's ability to work with AI, we can design specific assessment items, but you need to be authentic tasks that capture slices of the interaction. It does not need to be the whole thing, which will be very cumbersome and time-consuming to analyze and for the students to perform and compare. However, you can have slices of the interaction, such as just constructing the hypothesis set, such as constructing complete requirements that you can analyze, and try to use that to assess people's skill. And some ongoing work we have in each of this area. For example, been trying to broadening the population and broadening the outcomes. So far, we've been focusing on college students and user general public, but there are workspace professionals who are dealing with this as well. So I'm currently working on that project with Microsoft. And we can also consider other outcomes than productivity and quality of the output. There are many more, such as people's cognitive and affective changes according to when working with AI. And there's just like things beyond task outcome of productivity, efficiency. And we also try to diversify the domains and the baselines. For example, there's a project on calculus, which is the prerequisite of computing, possibly, like most likely. And we also try to compare it against the traditional instructions. Currently, we have baselines such as like non-existent instruction or baselines that people try to teach themselves by watching videos. But there are also other type of instruction focusing just on the more traditional parts of teaching procedural skills. What if I teach you how to write code? What if I teach you just how to solve these derivatives? How does that comparing to instruction that is trying to put forward more higher order thinking skills? And we also try to scale the automation for the formative assessment. How can we provide assessment in the fly, in real time, and help that, use that as a signal to help students improve during the workflow. So that's kind of all I have for today. Thank you for your attention. Let me know if you have any questions. Yes.
Yeah, so you've built these great tools. They look very, very good. And you've kind of said, hey, if you want to instruct students about debugging or about requirements writing, these tools are very effective ways to do that. So, as an instructor, I hear this and say, okay, yeah, I would love to teach these things. But we have an existing course that is already filled with many computer science topics. And to fit these in, we might need to deprioritize other things. So I'm curious what your thoughts are there. Like, what should we deprioritize to be able to fit these in? And if Hippocampus was used in a CS1 course, how did they fit that in? Like what changes were made to the courses?
Yeah, totally. So the calculus project I was mentioning about is kind of trying to exactly do that. So the alternative is like procedural problem solving, because we have all this exercise that help people practice on solving equations. You have a problem set, you're trying to manually compute the critical points, compute the derivatives. However, you can also have exercise that is trying to put people's thought more on coming up with hypotheses and different scenarios to test and verifying the generated response. So in within CS1, I think it will be a similar story. You could spend a time asking students to write code, to trace code, to do all the stuff, or you can also spend some time helping them think about the hypothesis space of where a program can go wrong, how can they reason about bugs, like the mistakes, like a test-driven development case. Without doing experiment, it's hard to say which one is more effective. We're currently doing it. Our hope is that people may get less good at, right, like procedurally solving the problem because they just not practicing it enough, but they will be better able to use AI to perform stuff because they are better able to verify AI output and better able to communicate their requirements.
And just a quick follow-up. So when you're saying that we should teach these skills, do you think that it makes more sense to do this throughout the curriculum over many years, or is this something that we mainly target people early in their computer science education or later? Is there any literature on that?
I don't think there's a sequencing literature yet, or like, how do you design your whole CS major curriculum roadmap? Yeah, but that sounds like an interesting topic to investigate. My lean is that it's difficult for people to learn something. If you want some concept to land in their mind, you need to repeatedly introduce it. So it will be better if you have it introducing different classes in different format, because what does a requirement mean and how does this hypothesis space for verification look like will be different depending on your different computing disciplines. So you need to be able to kind of reintroduce the idea many times in order to connect the dot and see the higher level. Okay, I need to communicate and evaluate. But with each specific application, it will look different. Like with app development, with CS1 level problems, with data analysis, with some sort of other disciplines, it's very different.
Makes sense. Thank you.
Mm-hmm. Questions there or?
I have a quick question concerning to the slide before this slide.
Okay.
So when I look at the skills, it seems to me, it's ironically, this is to me, it's more like a communication department or business department, very general skills for people to learn. And I do believe they are very, very important. I want your take on what specific sets CS department apart? It used to be computational thinking or whatever it is, but now look at the skills. I totally agree with these skills are very important, but to me, it's more close to business or communication department than sets the CS department apart.
So what is computational thinking? Yes, so this is a question that people have been discussing as well, right? Like communication and evaluation will mean, as I kind of suggested in my answer to the previous question, in different computing discipline, this already means different things. And for sure, for a different domain, like communication business or versus computing, this will mean different things as well. So a designer can communicate and evaluate their artifact. A business people can communicate and evaluate their stuff, their business plan, their investment strategies, and computing people will be communicating in terms of, for example, software requirements and validating in terms of the test cases. So these are, I agree, very abstract keywords for succinctness sake. We are keeping it that way. However, when you operationalize it and when you look into the specific study in a very specific context and population, it will be manifested in a more computing-related way. And the study that we were doing and we were conducting is related to programming and having people actually develop program artifact with AI, and the things that we teach them is related to that as well. Cool. Seems like there's no more questions.
Thank you all so much for joining us today for our first LCI seminar. And let's just give a big another round of applause to Christina.